Hello everyone. Today my topic is online learning algorithm for hurricane intensity prediction. This is the outline of our presentation. First, I will give introductions about the hurricane intensity prediction problem. Then I will discuss our proposed framework, following by the experiment result and conclusion. Hurricanes are tropical storms with very high wind speed. Their potential destructive power can be measured by their speed over the maximum sustained wind. Based on the Saffir-Simpson hurricane wind scale, the hurricanes can be classified as category 1 to 5. The hurricane can produce severe damages when it strikes the land. For example, Hurricane Harvey in 2017, a category 4 hurricane, causes more than 100 billion damages and more than 100 deaths. According to the data from National Hurricane Center, high-intensity hurricanes of Category 3 or higher account for nearly 85% of the damages. Therefore, accurate prediction of high-category hurricanes are essential to reduce the damages and save lives. More importantly, recent studies has shown that climate change affects the frequency and magnitude of the high-category hurricanes. For example, Holland and Brunei estimated an increase rate of 25 to 30% of Category 4 and 5 hurricanes per centigrade due to the global warming. Balaguer also noticed that the magnitude of the rapid intensification also increases because of the climate change. In the United States, the National Hurricane Center is responsible for issuing warnings and forecasts of hazardous tropical weather conditions. They issues official forecasts, including trajectory and intensity, up to 120 hours in advance. Here's an example of official forecasts produced by the National Hurricane Center for Hurricane Dorian in 2019. In this figure, the yellow circle refers to the current location of the hurricane. The figure also shows the forecasted locations and the intensities of the hurricane at a 12-hour interval for up to 5 days. Thus, the hurricane prediction task can be viewed as a multi-lead time forecasting problem. The figures below show the forecast scales of National Hurricane Center over the last 30 years. The left figure is a trajectory forecast and the right figure is the intensity forecast. In both figures, the y-axis shows the prediction errors. As can be seen from the figures, although trajectory forecast has been improved considerably in recent years, there has not been much improvement in intensity forecasts. Therefore, hurricane intensity prediction is still a challenging problem. In this work, we cast hurricane intensity prediction as a multi-lead time forecasting problem. Formally, the problem can be defined as below. Suppose T is our current time and YT is the current category of the hurricane. Our goal is to predict the future category at time t plus 1 using predictor xt1. Then, we predict the future category at time t plus 2 using predictor xt2 until xt plus capital T. When the current time becomes t plus 1, we will produce the same set of predictions. Choosing a good predictor is very important. Some previous works implemented with historical data as predictor, which can only be applied on short lead time prediction tasks. It is because that the historical data is insufficient since the model does not explicitly capture the current dynamics of the physical environment. Another choice is using the physical model output. The physical model uses supercomputers with mathematical modeling of the meteorological data. It produced more accurate forecasts, but it also has some limitations, like computational expensive, and also the accuracy of the individual model depends on the model parameterized and assumptions. As multiple physical models are available at every time step, Ensemble forecasting can be used to produce the final forecasts. There are several limitations for the current ensemble algorithms. First of all, they are not designed for ordinal data, such as hurricane categories. Second, they are not considering the importance of correctly predicting high category hurricanes. To handle the ordinal data, we can define our prediction loss based on subvector ordinal regression algorithm as follows. Assuming we have 3 categories and 2 thresholds, B1 and B2. If our prediction is in the correct category, the loss is 0. If a prediction is at a lower category, the loss is epsilon star t tau. If the prediction is at a higher category, the loss is epsilon t tau. The prediction loss can be easily extended to quantile loss as follows. With the same examples, if the prediction is at a lower category, the loss becomes psi times epsilon star t tau. If the prediction is at a higher category, the loss becomes 1 minus psi times epsilon t tau. The hyperparameter psi is typically chosen as 0.9. In this case, the prediction at a higher category obtains much lower loss. Therefore, the model prefers the prediction of a higher category instead of a lower category. Now I will talk about our proposed framework, Omulate OR and Omulate QOR. Our goal is to predict the hurricane categories using forecasts generated from a multi-model ensemble with multi-lead times. Each forecast is generated using linear prediction with a learned weight vector. The Omulate OR framework is an extension of our previous Omulate framework, which was designed for hurricane trajectory prediction. It is an online learning algorithm and also produces multi-lead forecasts. The Omulate OR framework also applies the backtracking and restart strategy. When new observation is obtained at time t, restart the learning process from time t minus capital T. Then repeat the weight updated process till time t. This is the objective function of our Omulate OR framework. The first term is a prediction loss based on the subvector ordinal regression algorithm. The second term is a task relatedness with different lead times. It is because we do not want the weights for different lead times are very different. The third and fourth term are online learners, controlling the weight changes from previous round. The last term is a regularization. For Omulate QOR algorithm, the only difference is that we changed the prediction loss with quantile loss. Now let's discuss our experimental results. We performed the experiment using real-world hurricane intensity data from various sources. The ground truth hurricane intensity data along with the official forecasts are obtained from the National Hurricane Center, while the ensemble member forecasts are obtained from the UWM website. We collected the hurricane intensity data from the year 2012 to 2019, which contains 257 tropical cyclones. Each tropical cyclone has an average length of 23.2 time steps. There are 21 intensity forecast models used in our experiments, which are a subset of the models used by NHC in the preparation of their official forecasts. The data from 2012 to 2016 are used for training and validation, while those from 2017 to 2019 are used for testing. From the result table, the NHC official forecast has the best performance. As previously noted, the NHC official forecasts were generated from a larger suite of dynamic and statistical models, some of which are not available to us. Besides the NHC official forecasts, our Omulate OR and Omulate QOR methods clearly outperforms other baseline methods for all lead times and all categories. We also investigate the effect of using quantile loss. We calculated its MAE for different value of psi. Note that Omulate QOR with psi equal to 0.5 is equivalent to Omulate OR. The result clearly shows that increasing the hyperparameter psi generally leads to smaller MAE value for high categories. This result confirms our expectation of using quantile loss to improve the prediction accuracy of the high category hurricanes. Let me give our conclusions. In this paper, we present a framework called Omulate OR for online multi-lead time hurricane category predictions. Our framework employs an ordinal loss function to handle the category data. Experimental results show that Omulate OR outperforms various state-of-the-art online learning methods. In addition, Omulate OR framework can also extend it to accommodate a quantile loss function to further improve its prediction accuracy for high-category hurricanes. Thank you for listening.